Hello everyone. Today's lecture we are going to discuss about disjoint set data structure. Disjoint set data structure primarily concerned about the operations of different sets of elements which are disjoint. But in particular we will see how union, make set and find a representative element of a set, these operations are performed. These operations are widely used in different applications, some of which we have already seen in the graph algorithms. For example, finding the connected components, or whenever we are trying to join two disconnected components of a graph, we often use the union operation of the two disconnected set of vertices. So today we are going to see how these operations can be performed efficiently by using suitable algorithms and see its implications on certain applications. If you remember correctly that we have used this disjoint set data structure earlier when we studied minimum spanning tree of a graph. A minimum spanning tree of a graph is a tree which comprises of every nodes in the graph whose sum of the edge weights of that element of the edges in the tree are minimum. And we have seen that we used Kruskal's algorithm to find the minimum spanning tree of a graph. So what do we do is that for each vertex, initially we identify each of the vertex as a different set of elements. So initially each vertex is particularly belongs to one set. So the representative itself is the vertex. Then when we try to see that this is my minimum edge, then we try to make union of two vertices and form a bigger set. So in the next iteration, we take the edge and join these two vertices and form a bigger set. Simultaneously, we proceed in this way to find the next minimum weight of the edges and then find the next vertices which we could join. And gradually we proceed to find the minimum spanning. Now if you remember that there are certain operations which we do which are basically related to the operations over disjoint sets. For example, whenever in this graph we tried to choose the edge 3, then we found that this edge belongs to the nodes of two different components. One is this and one is this. So we can add this edge here. Now whenever from this, if we want to add this edge, now we see that this edge forms a cycle. And one way to determine that this edge forms a cycle is already before addition of this edge, we have this graph already available as a set of vertices to us. Now whenever we are trying to add these vertices together, then we are essentially making another connection between a particular set of vertices which already belongs to one set. Now this would form a cycle. So now we could see that instead of adding this one, why we have added this one, since it does not form any cycle. Now if you look at the algorithm, we have used certain kind of disjoint set operations. First of all, when here we made for every vertex individually we make sets, different disjoint sets from them. Then whenever according to our edge weights, we try to find that whether two of the vertices belong to the same set or not, as in this case these two vertices belong to the same set, so we cannot add. If they does not belong to the same set, then only we can add these vertices, so that they could not form a cycle. Now whenever we could add those two vertices, then we join two different disjoint sets and form a union of them, and that is done by this union operation. Now given that there are, let's say in this example we have 4 elements present in a set, so therefore we need to name this set as one representative element. For example, let us this be the representative element of the set. So whenever I say find the set where these elements belong, I always give answer to the name of this element, which does the find set do. Now, when I try to make an union, whatever be the elements that I give, after union, the whole set forms together and gives me back the representative element of the whole set. So that is what the union operation does here. So first of all, we need to make disjoint sets by this. Then we need to see whether cycle is being formed or not. If that is not a cycle, we add the edge to the spanning tree and make two disjoint components together with uniting those two sets. So therefore, there are use in this make set, find set, and union operations. And as you know that the complexity of this algorithm is order of E log V as discussed earlier, but it is totally depend on how do we perform or how efficiently do we perform the make set operations, the find set operations, and the union operations together. So let us see that how do we design such operations. So therefore, in summary, disjoint set data type comprises of particularly three operations. One is make set, one is find set, one is union xy, where make set x makes individual element sets. Find set x returns the representative elements where this x belongs. For example, if you have a set of 1, 2, 3, 4, and I say my set is being represented by the number 2, then if I say find set 4, it will give me back 2, as if 2 is the name or the representative of that set. So if I give 3 also, it will give back to 2. Union means if I give an element of a set with another element of another set, then if those two sets are disjoint, so basically they will make those two sets together and form one union of both the sets. Here x and y may not be the representative of that set. If that is the case, that x and y are not the representative, then we find the representative where x belongs and where the y belongs. So find set of x and find set of y are implicit in the unions. Effectively, these three operations that we discussed just now, we want to make it efficient, and our performance parameters are, since as I have said that union and find set can be done together sometimes to find the representative and then make a union. So we will assume that we make m number of calls to union and find, and we have n elements to start with in the beginning of the set. One of the applications we have seen here is to find the minimum spanning tree, where we use disjoint set. But wherever you can find there are connectivity which is related to two disjoint parts of the graph, disjoint set is one of the choices. For example, for dynamic connectivity of initial graphs, when you try to add a node u, then essentially you make a make set operation. When you try to add an edge, that means you are trying to join two different sets, then you make an union operation. If you try to see whether u and v are connected, that means you are trying to find the representative where u belongs and you are trying to find the representative where v belongs. If both the representative are same, then they belong to the same component or they are connected. So therefore, representative finding for u is just a find set operation, and here we make two find set operations. So this way we can see that there are many practical applications of this disjoint set. So therefore, all the bottlenecks of using this disjoint set lies in finding union and the find set operations in an efficient manner. We will see how do we implement this in future slides. Let us first think about a simple implementation of this disjoint set operations using linked list. So in a linked list, suppose we have a set A which is given as 4 elements C, H, E and B, and let's say C is the element that is basically the representative of this set. So what we do is that we have a linked list where C points to H, H points to E, E points to B and so on. And then To make that, whenever we have a find set operation, immediately we get back the representative element of the set as C. We also have back edges from H to C, from E again to C, from B again back to C. What does it entail is as the fact as follows, that if I try to see the find set E, I will get back the element C, which is the representative as per my definition. If I say find set H, I will get back the element C in just one step, because now the link has been pointed. Now the question is that if I have to make an union between two such linked list representations of disjoint set, what we can do is that we can simply put the end pointer to the beginning of this set, which is done here. And then the rest of these pointers back to the representative set C should be pointed back to a same representative, which I assume that the representative be F. So therefore, for all these nodes that I join after the set B to make union, all of them, the back pointer is again should be linked back to the node F. So therefore, if you look carefully, that make set operation is obviously order of 1, because make set operation is done over individual elements of a set, and when you try to do that, you only create a particular node, so this operation is order of 1. Now when you have to find an element or make a find set of X, it is order of n, because however you find, you need to traverse through the list and find that element, and after find set through this link, you need to get back the representative of that set. So therefore, traversing the entire list in a worst case would take order of n. And in union, you can easily see that the whole set I need to make at the back of the first set, and all the pointers that were earlier pointing to the representative of this particular set as C, all of them has to be point back to a unique representative in the union set, that is F in our example. Therefore, in the worst case, the number of elements that we joined, all of them or most of them has to be put back to F, and therefore union xy, we will see that the order of n operations, because those back pointers that we are putting back to the representative element F. So this makes these three operations. So if we implement it using single linked list, then this makes that three operations respectively as in order of 1 and order of n for find set and order of n for union. So this is one particular implementation how we can use it, but can we do better in this order of n times? Let us see what are the variant implementations we can have. Instead of using linked list, we could have also used an array and seen this kind of sets after joining or a set of elements as a tree-like form. For example, if you look at this tree, it says that I have 4 element set, disjoint set 8, 9, 4 and 3, and the representative of the set is 8. So this is the representative of the set. Now I have another disjoint set here, which is 7, 0, 5, 2, 1 and 6 elements, and I say that the representative of the set is 7. So in terms of a tree-like data structure, we could use that at the end the root of this tree would be 8 and 7 respectively. So in an array, what we will do is that, so for every element, let's say for 0 here, 0 is pointed to 7, so we write 7 here. Similarly, 1 is pointing to 5, so we write 5 here. So the array here itself says that the element, the parent of that element is stored in the array. Now, for the root element, since there are no parent, we usually follow two approaches. One, we self loop it back. So we could say that the parent of 8 is 8, or we could say that the parent of 8 is 0 in case that we want to suppress the self loop for brevity. So we will say 0, and we will use this 0 notation throughout this implementation of the union set operations in this lecture. So in our case, we do not assume self loops, but we assume 0. Now, why do we form such kind of a tree? Because initially, when you tried to make set of each of the elements from 0 to 9, so each of the elements individually forms a set initially. So 0 is 1, 5 is 1, 1 is another set, 9 is another set, and so on. Now let us say I have a join operation or union operation of 1 and 5, which makes these two together as a set. Then let us say I have another union operation of 6 and 5, which makes these three together as one set. And this way I grow upon building this tree. So in generic sense, suppose I have two such different disjoint unions. One is this one is this one. Now if I want to make union, if I say I want to make union of 3 and 5, so 3 belongs to the set which is represented by 8. Similarly, 5 belongs to a set which is represented by 7. So if I want to make the union, then those two representative elements should be connected via a link. In this case, I make the parent of 8 as 7. So therefore, in the array, the parent of 8 here will be changed to 7. Similarly, these all union operations just do the same thing, because when I say I make union of 8 and 6, 8 is in this set, 6 is in this set. So again, I have to find the representative and make connections between them to form an union of the whole. So therefore, there are certain properties of this kind of array representation. First of all, the total number of zeros in the array are the number of disjoint sets. Why? Because the number of zeros is dictated by the number of roots there in the sets. So this contributed 1 0, this contributed another 0. So therefore, we can see that 7 and 8 are the two nodes that contributed 2 zeros. So we have two different disjoint sets. So according to our notions, where we are removing self loops and putting null pointers as zeros, so the number of zeros or there is no parents are the number of disjoint sets. Whereas if you see that after union, if we try to find out what happens, you will see that since parent of 8 has been pointed to 7, so now there are only 1 zeros because this has been converted to 7. So since this has been converted to 7, the position 8, now we have only 1 0. So this is only one disjoint set now. Let us see how does find set operation do. So in the worst case, if we do not think and link it, if we link it in a naive manner as we have seen here in this case, in the worst case, what can happen? Let's say I make union of 1 with 2, then make union of 2 with 3, then make union of 3 with 4, and so on, and then finally make union of n minus 1 with n. So I will get this kind of a structure as shown here. Now in this structure, if you proceed, you will find out that if I want to find so the representative after this whole structure is formed is n. Now find set operation gives back me the representative. So if I want to say the find set of 1, it will give me back n. And how can I get that? I have to traverse through every element in this chain and find back towards n. So therefore it will take order of n in the worst case to find where an element belongs or to find the representative of an element. How does union of two elements fare? So suppose I have this kind of chains. Now union operation has inherently two find set operations within it. Because if x and y are not the root, then I need to find out the root or the representative element to get this x and y and then link between them. So therefore, since I have involved find set operation, so union operation in the worst case also cannot be easier than order of n, and this order of n is basically due to the find set operation that we perform in the union itself. So here also see that if we use the array and store the parents of each particular set elements, it also does not help if we use linked list in the earlier case, because my find set and the union both operations are being performed in order of n manner. Can we do better? Of course we can. That's why we need to do a little bit smarter when we do the union and find operations. Let us see. First of all, here in the previous case, when we say we are doing an union, we are not looking into the disjoint sets, how many elements are there, how this tree or how much depth of these trees. Rather, we are naively forming a connections between these two sets to form an union. These connections we are forming naively. Can we do by looking into the size, which we say that a smart disjoint set operations where we make the union by size. Let us see how we can do that. Suppose we have one particular disjoint set of size 4 and another disjoint set of size 6. Now when we are trying to make an union of 3 and 5, that means we are trying to make an union of these two elements. So essentially this is the representative element of this union and this is the representative element of 5. So we are essentially trying to connect 8 and 7. So when we are trying to connect 8 and 7, we will try to make the parent of lesser sized node to the higher size node parent. So therefore, since this part has size 4, this whole part, so we will try to point it to the higher size set with the intuition that this might be reducing our find set operations, because if we do the other way around, then this set, since its size is more, its height would have been more than this set in a normal or in a average cases. So we might have more depth to visit for find operations. So this is what do we mean by union by size. So we maintain a tree size, the number of nodes for the root nodes, which is 4 here and 6 here. We link the root of smaller tree to the root of larger trees. And if both have the same size, we arbitrarily break it. Anyone can be the parent of the other if both sizes are same. So how do we do find set operations there? So if we are given an element x, for example, in this tree, if we want to find set of 6, then what we will do that while this element is not the parent, I will gradually go towards the parent. So I will assign x to the parent, I will assign x again back to the parent, and so on. And finally, if this is the parent, then I will return this as my representative element of the set of elements where 6 belongs. How do I find that this is the parent? The parent array in this index would contain a 0 as our representation. Make set is very simple because each of the individual element we make different sets of each elements, where the parent x, that is each element, is a different disjoint set. So the parent pointer is null, or in the array it is 0, and its size is 1. Union is tricky, as we have just discussed in an example. So if we have to do an union of x and y, first we try to find out the representative elements of those x and y where it belongs. Now if the representative elements are the same, then there is no need to perform an union. For example, let us try to take the union of 5 and 2. If I try to take the union of 5 and 2, the both represents in the same disjoint set. So the union would be already computed and the representative is rooted by the node 7. So therefore, we just return R in this case. However, as we have just discussed, that if the size of one set is more than the size of other, in case that R is not equal to S, that is the else if part. So if one size is more than the other, then we try to make the lesser size parent pointing to the more size representative element, as we did here. And then we add the size of both the elements to form the set together, and then return finally this element as R. So we return R. The other case, we make the parent of R towards S instead of this case where we made the parent of S towards R. Then the rest part is the same apart from returning the S. So in a nutshell, that the lesser sized set, the representative or the root of the lesser size set would be connected to the root of the higher size set during union operation. Now, what do we gain by that? So one of the fact that we gain by that is as follows. First of all, if we try to analyze that what happened in case of find set operation, we need to analyze that what is the maximum depth of or the height of this particular tree structure that we are building through union. So here is a property. Using union by size, for every root node R, we have size of R at least 2 to the power height of R. So it means that, let's say here, if the height is 2 for a particular node, then we will say that the number of nodes in this particular tree rooted at R with height 2 is at least 2 to the power 2 or 4. How do we prove it? Base case is very simple, where my size is 1, that is the number of node is 1, and the height is 0, so 2 to the power 0 is 1, so 1 greater than equal to 2 to the power 0, it is proved. For inductive hypothesis, assume that it is true before I do all the first I links to form the union. Now, when I say that when I make a union, what happens? Only the roots of the tree changes, and the roots of the smaller sized disjoint set tree, the parent of it gets pointed to the higher size root. So tree rooted at R changes only when a smaller or equal size tree rooted at S is linked to R. So there are two cases possible while linking. One is the case which is this one, where we have the height of the disjoint set rooted at R is more than the height of the disjoint set rooted at S. So in that case, at the end, if we say that the size of the whole set of elements rooted at R after this connection has been made, is size dash R, it is obviously going to be greater than size of R because we are at least adding some nodes. And due to the induction, we know that size of R is greater than 2 to the power height of R. And since this has more height, the height of R is more than the height of S by this relation. So the 2 to the power height of R is obviously 2 to the power height dash of R, that is the final height of this set, because I know that the height of this set is less than the height here. So after joining this one, definitely the height will remain as it is. So it proves that the new set of elements also adheres to the 2 to the power height r bound. At least 2 to the power height r elements should be there. What if the other condition happens? If the other condition happens, as you can see here, the number of nodes in S is less, but the height is more than here. So according to our union by size, we will make the less number of nodes point back to here. So the final size will be the size of the set represented by R or rooted by R, and the size of the set represented or rooted by S. Now, as we can see here, is definitely the set rooted at this S has less number of nodes than this. So therefore, this is greater than 2 into size of S, because size of R is obviously more than the size of S. So this is greater than 2 into size of S. And now, since size of S is follows the induction principle, so I can say that size of S is 2 to the greater than equal to 2 to the power height of S. So if we solve this equality, we get 2 to the power height of S plus 1, which is the new height of R, because this height is more or equal to this height. Now when you link this edge from S to R, you obviously increase the height by 1, and that is why this inequality holds. And hence we have proved that for a particular root node R, we can say that the size of the elements in the disjoint set that is represented by that root R is at least 2 to the power height of R. And you can easily assume that this has a very interesting ramifications with the find set operations. As I have said that the size of elements pointed at a root is obviously bounded by 2 to the power height r, therefore my height is obviously bounded by at most log of the number of elements rooted at r. So therefore, immediately we can find out that union and find set operation can take log n time, because union by size, a tree of n nodes can have height at most log n. So therefore, since my height is bounded by log n, so whenever I am doing a find operation with, let's say I am trying to find this one, so I need to at most traverse this many number of nodes, that is the height of this tree. So it is bounded by log n, so I have to traverse log n times to get the representative or the root element. So union operation, as you can see, is just a link transfer from a smaller size set to a higher size set, except it needs to call find set. So, and find set, we have found that it is bounded by the height of the tree, so it is log n. So therefore, if there are m number of union and find set, in a total we will take order of m log n time. So essentially this is an improvement, because earlier here we got order of n. So instead of this, if we union it by size by a little tricky method, that we will just add the lesser size element parent of that representative set towards the higher size element representative, then we get this benefit. Can we do something else with the array representation? Instead of, it is obvious that you might have already thought about it, that instead of looking into the size to union, to make union or join to disjoint sets, why don't we also look at the height, which we will now discuss, which we call by union by rank. Essentially we mean rank as the height. So what we will do is that this particular disjoint subset containing of 4 elements with the representative element 8 or the root element 8 has height 1, as you can see here, whereas this has height 2, as you can see here, it has 6 elements. Now when we try to make a union, so you can see that the make set operation is just the same because it only makes sets of individual elements. Find set operation is also just the same because it just tries to see a path towards the root and finds the representative element, that is the parent of that particular disjoint set data structure represented in a tree or the root node. The only difference is that in the union operation. So if we try to make an union of 3 and 5, so what we are trying to do is that we are trying to first see where this 3 and 5 resides. We find it that 3 resides in the set represented by 8 and 5 resides in the set represented by 7. Now instead of union by size, now we are doing union by height or rank. So the smaller height will be pointed back. The parent of the smaller height disjoint set root will be pointed to the bigger or the longer height disjoint set root. So 8 is pointed back to 7. This is what union by height does. It is very interesting to see that there are certain properties that gets introduced by this. First of all, let us look at the union algorithm. So this is just finding the representative or the root element of that particular disjoint tree. Now this is if they belong to the same we have discussed. Now if a height is more than and or equal to that, if it is more than, then obviously that the parent of S will be pointed back to here as we did here. If it is equal to, then it means that both the ranks that we are making union are the same. So therefore it's a tie. So what we have to do is that in case of a tie, we just increase the rank by 1 because we do the same thing, that is we make such kind of a connection as we have done here, but we increase the rank of R by 1 because obviously two height ones, if one parent is pointed to another height one or rank one's disjoint set the root node, obviously that root node rank increases or the height increases, and that's why that height gets 1 added to it. And finally we return R. This is only if both are equal, otherwise it is just we point it back. So if the rank S or the height of S is more than the height of R, then we do the reverse thing as opposed here. So let us now analyze that this kind of heuristic, instead of by size, if we do by height or rank, how does it fare? So first of all, some simple properties of this kind of heuristic. If X is not a root node, then the rank or height of X must be less than the rank of parent of X. This is pretty obvious. If you see that all the non-root nodes like this one, the rank and the rank of this one, obviously the parent of this has a higher rank than this. This is because such kind of links get created when we make union of two disjoint sets. So this kind of a link only gets created when we had made disjoint union of this set with this set first set. Now when we connect such kind of a link, so a rank k is created by linking two roots of rank k minus 1. So earlier when we are trying to connect this set and this set, both has rank same. Now since it is same as per our algorithm, when we try to point it back from this node back here, then we make this rank 1 increase by 1. Therefore, if X is not the root, the rank of X is obviously less than the rank of parent of X. If X is not the root, then rank of X will never change. Why? Because see, if there is another disjoint set for which we need to make a joint here, we always look for the parent node of this disjoint set. Therefore, all the nodes that are not the parent or not the root node rather do not make any changes. So therefore, their rank never changes. So X is not the root node. If that is the case, then the rank of X will never change. If parent x changes, then rank of parent x strictly increases. Let us look back to the union. Parent of x, let's say for this example, here the parent of x8 is getting changed by an union operation. So if this gets changed by an union operation, so earlier this parent of x before union was 0, now after union it becomes 7. So once it becomes 7, therefore either in case of join its rank always increases, or it will remain at 0 if it becomes disjoint, and this becomes a representative root. So therefore the parent can change only for a root, because we are only linking roots to make union of disjoint sets. So before linking, parent x is equal to 0, and after x is linked, so after x is linked by union by rank, the new root R has obviously have more rank than the rank of x. Now comes an interesting property which says that any root node of rank k has at least 2 to the power k nodes in the tree. For example, any root node, let us see that this is a root node in this tree of rank 3 here, because after this link has been performed, the depth is 1, 2, 3 is the depth. So after this link has been performed, my rank becomes 3. So what I have to prove here is that I have at least 2 to the power 3 or 8 nodes in the tree. This also we can do as we have done earlier using induction. So for k equal to 0, that is only for rank 0 or 1 node, it is basically true, because 2 to the power k is 1. So I have 1 node in the tree, obviously. Let us assume that it is true with k minus 1. Now let us try to see that how this union by rank algorithm works. If this height is less than this height, then only we perform this kind of link. So this link is then only made. So if this height is equal to the height here, then also we will make this link, because ties are broken arbitrarily, and the rank of this node is increased by 1. So therefore, the only when a root node increases its rank is basically when we try to join two different disjoint set having same height. So therefore a node of rank k is only created by linking two roots of rank k minus 1, and by induction each root of rank k minus 1 or the subtree rooted at k minus 1 has 2 to the power k minus 1 nodes. So after union, the resulting tree should also have 2 to the power k minus 1 nodes. So this concludes the proof. Now this is very interesting proof, because it says that the root node in the disjoint tree having rank k has at least 2 to the power k nodes in the tree. Therefore, it immediately concludes this part of the property, that the highest rank node is the rank of the highest rank node would be less than equal to floor of log n. It immediately comes from property 1 and property 4, because property 1 says that if x is not a root node, then the rank of x is obviously less than the parent's rank, and we are saying that the highest rank possible is, so therefore in any path if you go, so if you go via any path, the rank of x is obviously less than the rank of its parent, which is p of x. So if you go through any path, it happens. So therefore, since this inequality happens, So the maximum rank we get at root node, and we can say at by property 4 that any root node, we can say at property 4 that any root node is of rank k will have only 2 to the power k nodes in the tree. So therefore the highest rank node is root node by property 1, and it has this highest rank node rank would be bounded by log n, since at least 2 to the power k nodes in the tree should have. So it immediately follows that the height of the tree is bounded by log n. And therefore, if you first look at this theorem, therefore all the union and find set operations is bounded by the height, and the running time, since it is bounded by the height, is order of log n in the worst case. So union by rank is similarly in terms of time complexity is of similar nature as we have done union by size. Now there is another interesting property that we will use in the future, that for this union by rank heuristics, that for any integer k greater than 0 there are n by 2 to the power k nodes at rank k. We can prove it in many ways. One of the proofs can be done by contradictions. However, since we have proven many properties earlier, we will use that property to find the proof of this. First of all, any root node of rank k has 2 to the power k descendants. We just proved it in property 4 that any tree root node of rank k has 2 to the power k nodes. So therefore, any root node of rank k must have 2 to the power k descendant. So this node must have 2 to the power k descendant. What about the non-root nodes? We claim that the non-root node of rank k also has at least 2 to the power k descendants, because it had the property that the same property, let us consider about this node. This node also had the same property just after it makes this link to the root by some union operation. Then the property of this particular part of this node doesn't change. So therefore, this also, the any non-root node also have the same property, because it just before it becomes non-root, it had the same property, and its rank does not change anymore once it becomes a non-root node. And its sets of descendants also does not change once it becomes non-root. So this part also does not change at all. Different nodes of rank k have common descendants. Cannot have common descendants, as we can see in this figure. So this is also by property 1, which says that the rank of a node is less than the rank of its parent. Therefore, different nodes of rank k cannot have common descendants, otherwise this property 1 would have been violated. So this proves that every node has 2 to the power k descendants. So therefore, for any integer k, if a node has rank k, then obviously if there are total n number of nodes in the tree, so it must have to be bounded by n by 2 to the power k, otherwise we will reach a contradiction of the total number of nodes to be n. So this is a very interesting property which we will use when we gradually refine our union by rank or union by height heuristics in the future slides. So as we have seen that union by size as well as union by rank does not give the find set and the union operations less than order of log n time. So can we do better? So in terms of doing better, what are the fundamental things we can look for? Let us say that suppose in this particular set we are trying to find x. Now when we are trying to find x, then how do we find x? When we try to find x, we try to see which is the parent of x, its parent, and gradually this way we come back towards R. And once we find the root, we declare that this is the representative of the set where X belongs. Now you can see that again, if we have to make another call, let's say to find U, then we redo this all steps together. That is, from U again, we go back to this V, then to this W, and then to this R to finally declare the find set. Rather, what we can do is that since we found a path from X to U to V to W to finally R to make the answer to the find set, while climbing this way, we directly point back to its parent towards R so that the subsequent find operation calls to U, V, and W gets less time consuming. So that is the philosophy of why we use path compressions when we use the union by height. So when we do a find set operations, all the parent nodes apart from X. So when we do a find set, when we found that the X belongs to a set which is represented by R, we immediately point back to this element. Similarly, in the path, all the elements that we found out while traversing to R, we all put back those elements directly to the element R. So that in next iterations, if we try to find those elements, we could find it in a very efficient manner. Let us try to explain this concept with an example in details. So consider this graph. Suppose this is my X element, which I am trying to find. So when I am trying to find this element, what I will try to do is that I will find this element via this path, then I will go via this path, then I will go to this node, and finally I will go to root and tell that R, or the node marked at 0, is the representative of the node marked at 9, which is X. So the find set operation recursively will try to do the following, that first it tries to make the parent of the node that we are trying to find directly there. Now I will make the X to the parent node, that is this one. Now my X is this. In the second iteration, similarly by recursive manner, we will point this parent back here and point back to the next level parent here as my X. Recursively again, this will be point back here. Next level parent, this one will be my next X. So now my X be this one. Again, what I will do is that recursively point back here. So the parent is now the root itself. When I come back here, I stop my algorithm when I found the parent is root itself. So you can see the philosophy of path compression. This is the way in which we do that. Throughout the path, wherever we found a node, we directly connected the parent of that node directly to the root of that particular disjoint set. And it is realized by this recursive algorithm where we do that the parent of X is recursively called upon the parent of X, and finally we return the X, and we do it until X is not the parent. There are a few points to note here before we see in the analysis that how good or bad we performed here. Number one, please note that while trying to do this path compression, we are not updating the height or rank of any node. Number two, we are neither deleting any nodes while doing this path compression. So the final tree after path compression has exactly the same number of nodes as the initial tree. And all the ranks at each individual node remains the same, though their positions got changed or height get disturbed, but the rank value or the rank array we are not handling that here. We are not changing there. What we are doing is we are only changing the pointers towards the parent in a different manner directly towards the representative or the root of that cell. Therefore, if we try to jot down the properties, so first, the tree roots, the node ranks, and the elements within a tree are the same. So this is my property 0. So the tree roots, the node ranks, the elements within a tree are the same with or without path compression. Now this is a new property that we need to prove because we are changing the rank, we are changing the parents, the link of the parent. So if x is not the root node, then rank of x should be less than the rank of its parent. Though we have proven this earlier, but due to path compression, since these parent pointers are getting changed, you can see that what happens that every node is finally pointed back to the root in this path. So therefore, this node's parent is obviously after path compression would have higher value if it would have directly if it would have been directly joined to the node R, then this has obviously the higher ranked value than it already had. So therefore, throughout this path in which we propagate up towards the root, the rank increases. So this new links that we are making, the parent values, the ranks of the parent values are also in the increasing way. So therefore this property, so path compression can make x point to only an ancestor of parent x. So ancestor of parent x obviously has higher rank. So therefore this inequality still holds. This is just like we have proven with union by rank, because if x is not a root node, then rank of x will never change, because we are not changing rank of x, we are only changing pointers in the path of finding some element and making it directly attachable to the root. If parent x changes, then rank of parent x strictly increases, because path compression doesn't change any rank, but it could change only parents. And parent x does not change during path so if you see these 2 points, then parent x does not change during path compression, the inequality continues to hold. If parent x changes, then by property 1 we have already proven that this has already been changed. So we have already proven that the rank increases even if we switch the pointers to the parent, because it points to the ancestor node. So the property 3 holds. Property 4, 5 and 6 are just the same as union by rank, because it only deals with the properties of ranking properties. So it only deals with the properties that that involves rank, and we do not change any rank value. So therefore these properties holds. So property 4 says that any root node of rank R has at least 2 to the power k nodes. Rank k has at least 2 to the power k nodes in the tree. The highest rank node is bounded by log n, as we have proved earlier. And for any integer k, if there are n nodes, so the number of nodes with rank k are at most n by 2 to the power k, which we have also proved. So we are not changing the number of nodes, we are not changing the ranks. Therefore, the property 2, 4, 5 and 6 are still valid here. Whereas property 1 and 3 needs retrospection, and the retrospection only comes from the fact that the new links that we are making when we are doing path compression only enhances the rank of its parents. So therefore these 1 and 3 property also holds. Now comes the interesting question of what do we gain by this kind of path compression based approach. So let us try to analyze. Before analyzing that, we need to have certain definitions to look for. This is a new definition that we might introduce here, which we call as log star n. It means that this is 0 when n is less than equal to 1. And this intuitively means that the number of times I need to take log to make the quantity less than equal to 1. Which means that if I have 16, then if you take one time log, then it will be 4. If you again take a log, it will be 2. If you again take a log, it will be 1. So therefore, I need to take 3 logs to make 16 down to 1. So this is the minimum number of logarithms that I need to perform one after another to make the number less than 1 is what do we mean by log star n. You could also have a recursive definition of the same, because I could say that log star n is in the base condition is 0 when n less than equal to 1. So if I take one log and then go by this log star n, then it is 1 plus log star of log n. So this is the recursive formulation of log star, where we have performed one log, that's why we increase the number by 1 and do it. All of this, the definitions that we have done till this point, goes from the fact that we have this Ackermann function in our hand. So this Ackermann function is a traditional math function which says that if j equal to 0, my fj is equal to 1. Otherwise, it is 2 to the power fj minus 1. Now see the growth of Ackermann function. So f0 is 1, f1 is 2 to the power f0, which is 2 to the power 1. f2 is 2 to the power f1, which is 2 to the power 2 to the power 1. f3 is 2 to the power f2, which is 2 to the power 2 to the power 2 to the power 1. So the number of powers of 2 gradually keep on riding after one another. So if you look at this direction, now you will find that the inverse of this function is what we are trying to define as log star n, is the number of times that I need to take this log to make it reduce to 1. That is, since 2 to the power is keeping on rising or riding one after another with the increase in the Ackermann function index, so the number of logs will also increase to make it less than equal to 1. So that is what the essence of log star n is. Now, to analyze the union by rank with path compressions, I would request you to please go through it in a peaceful mind and think over it. I will give you the intuition that what we are doing in this analysis and where we are minimizing our time complexity than we had done with only union by rank or union by size. To do that, as you can see that this log star n has a bit significance, that if you go for 1, so the log star n is 0. If you go for 2, the log star n answers 1. For 3 and 4 in the both case, the log star n answers 2. From 5 to 16, the log star n answers 3. So what we will now try to do is that, so these are for all these ranks or the ranges of ranks, since the log star n gives me back one particular value, we will call it as groups. So therefore, group 4 corresponds to the rank values 17 to 65536 and so on. Now I will try to see that the largest group number in my disjoint set tree is bounded by log star n minus 1. Why this is the case? Because we have proven that the highest ranked node is bounded by log n. Since the highest ranked node is bounded by log n, therefore the largest group number will be bounded by log star the highest rank. So this is basically log star n minus 1. So I can say that the number of nodes, if I try to make groups of the ranks, then the largest group number that I can assign in the disjoint tree of any node is bounded by log star n minus 1. Why I am trying to come here? Because why I am at all interested in this value? Because I will now try to see that during path compressions, when we try to find a set, we obviously try to compress the path towards the root, I will try to see that how many number of operations or how many number of node switches a particular node or its ancestor has to make after path compression. So I will assign those many credits or those many changes in the node pointers and what is its complexity. That will reveal me that the path compression has this much effect. We are not yet in finding the final answer. Rather, we need another property with respect to group, that the number of nodes in a particular group G is given by this formula. So where Fg is the Ackermann function. Now, why this is the case? Now see, the number of nodes in a particular group G, we are saying that for any rank K, as per the property here, I have, sorry, not this one, the property 6. So for any nodes with rank K, I have at most n by 2 to the power K nodes. So therefore, for a node with rank R, I have n by 2 to the power R nodes. Now for a group G, how many ranks are possible? The ranks are basically a range, and that range is from Fg minus 1 to Fg. So therefore, the number of nodes for a particular group G is the sum over all possible ranks, the number of nodes that can hold, over all possible ranks possible within that range. And if we try to sum it up, if we use this summation of GP series formula and bound it to infinity, so we will get it is 2n by 2 to the power Fg minus 1 plus 1. So which is, if we cancel out the 2, which is n by 2 to the power Fg minus 1, and 2 to the power Fg minus 1 as per the Ackermann function is Fg. So we have proven that the number of particular nodes, the number of nodes in a particular group is bounded by the n by Fg number. Now here comes the intuition of the proof. Suppose I am doing a find u operations in a path. Now it proceeds in a direction through V, then to parent of U, and then to U as shown in this figure. So therefore all of them towards the root will be compressed and we will make a link to the paths from there and from here, again from here, all the paths we will make a link and so on. So therefore if V is root, a child of root, or if a parent of V in a different rank group, then the find of U only changes one pointer and links back to X. So we will assign 1 unit of time for this find set operation for path compression. That after this find set operation, due to path compression, U will be directly linked to X. Now if V and X are not equal, then in the case we will also have V directly linked to X as well. So therefore we will also charge 1 unit of time to node V. I request you all to get a feel of this and try to prove these two statements. Now the observation is the rank of nodes in a path from U towards X increases monotonically. This you can easily prove as per our prior properties. And once we can prove that, then we can easily see that for a node V in group G, V can be moved within a group Fg minus 1, because you have seen that in a group there are certain ranges of ranks. So what I need to know for path compression is that how many times a node gets switched. So a node may be switched within a group between all these ranks, or across groups towards compressed and finally finding the root to point. So therefore we will have the time complexity is governed for every node in a group, that movement across groups, and movement charges within the groups. And for every node we will do, so we will multiply with the number of nodes. So we have seen that for a group G, the number of nodes is this much. And we have seen there are, in the previous property, we have also seen there are log star n minus 1 number of groups. So therefore it is bounded. The movement across groups during path compression is bounded by log star n. And within groups, as we have seen, that this many ranks a node can switch into due to path compression. Now if you look at here, that this quantity, the quantity here, and this quantity, the quantity here, if you multiply with this quantity, these two is less than equal to n, as we have shown here. Therefore this comes as n log star. What does this mean? That if we have m union and find set operations, so these are not interleaved, so that's why we are doing together, because union may have find set. So union by rank with path compression, if we apply, then we will get m into log star n amount of time in the worst case. So in average, each find set, union and find set operations is taking order of log star n, which is a tremendous improvement, because earlier with only union by rank or union by size, we are getting, that is of the order of height, which is log n. Now we are getting log star n, and log star n is drastically reduces to 1, because it keeps on taking log until it is 1. So which sometimes also may be said as order of m, that is order of the number of operations, because log star n is practically less than 5. On a lighter note, if otherwise we would have more than the number of atoms in the universe if we take n so much, when log star n will be more than 5. So that's why we have drastically reduced these operations of find set and union when we use union by rank and path compression, and gradually made it towards a log star n time. So which is a drastic benefit over these operations. So in typical case, whenever we implement this union set data structure, we use union by rank as well as path compression in our implementation. So in summary, so let us summarize that whatever we have seen. So first of all, we have seen that union set data structures are primarily used in many applications. One of them we have already studied in finding minimum spanning tree. Also, whenever we need to find graph theoretic components, join them or make union, we always use those connectivity problems as union find operations. And these operations can be algorithmically made more efficient, more succinct. And we have seen that how this union set data structure is represented by linked list, which is not so efficient. Also, the naive array and the naive link without looking into anything also produces the same time complexity of make set as well as the union, which is order of n. Finally, when we come by union by size, if we try to make union by size or if we try to make union by rank, we effectively try to make the find set or the union operations and bound it with respect to the height of the tree, which is log n. And then when we use path compression, we have analyzed that this path compression gives us much better time bound, which can bound the number of operations in the order of log star n. And therefore this union set data structure is very efficiently solved using path compression. Thank you. Please send us your feedbacks and your queries. We will circulate a form, and later we will host online sessions to clear your feedback. Thank you.